Okay, so here's a question that's looking at crystal structure and looking at the stress and the strain on this crystal structure, assuming that the electrostatic bond between them is acting a bit like a spring. So it says, first of all, assuming that we've got a separation of R0, and then when it's stretched, a separation of R, write an expression for the tensile stress and the strain, and therefore the spring constant. So really straightforward. I suppose the only difficulty is working out what you think the area might be. But of course the area is going to be the circular projection on this. So with that in mind, part A should be straightforward. That's hint number one. So let's work it out then. Okay, the strain is going to be the force over the area. We have the force divided by pi r over 2 all squared, giving us 4f over pi r0 squared, so that's r0. The strain, of course, is going to be the extension divided by the original length. And the force constant K is going to be the force exerted divided by the extension, minus R0. Good, really straightforward. Part B, however, starts to get a bit trickier. It starts talking about we have an attractive force and a repulsive force. Sorry, an attractive energy, repulsive. Oh yes, sorry, it says here electrostatic energy. So we've got electrostatic energy and a repulsive force due to neighbouring ions. So what it's asking for here is it's asking for us to work out the constant alpha. It's probably worth noting, and this is probably your first hint, that the potential between the electrostatic potential is given by 1 over 4 pi E0 Q over R. And therefore the electrostatic potential energy, the EPE, is going to be VQ by whatever your charge you're bringing into this environment is. So you're also given this term down here, which is a bit tricky, and what to do there and how to use it. So here is the next hint. So hint 2 is consider what happens if this is, say, sodium, for instance, Na+, then what is going to happen around them? Then you have Na+, and then you have Na+. So what is happening on either side? And where is this attraction coming from? Okay, so how do we go about it? Let's get another sheet of paper just to build this up. Okay, if we consider just two of these ions together, a positive and a negative, the potential that these two feel is going to be 1 over 4 pi E0 Q1, which is E, charge in the electron, by E, but it's a negative E, and divided by R0, which is a separation between their centres. We therefore have the potential from one of them, but now we need the potential from the other one of them, because this is the potential of one. So this is the electrical potential energy. There. Now, as we start to move out further, we get another one sitting at 2R. So our potential there becomes now E times E again over 2R, and that's positive. And then the next one becomes E by E over 3r, but that's negative because now we have another negative charge in there, and so on and so on. Now, of course, this is happening on both sides of the r0. So we've got r0 happening there, 2r, 3r, but also we have the mirror image on this side. So therefore, we actually got 2 of those, 2 of those, and 2 of those, giving us a simple expression of minus e squared over 4 pi e0 1 over r. What do we have here? This is e squared over 4 pi e0. Sorry, that's 2 over r, isn't it? 2 over r, 1 over r, e squared over 4 pi e0, 2 over 3r, etc., etc., as we go out. Now, this is where we start to link in this idea of the ln2, because as you see, what we're doing is we're coming along here, we just need to put it into those terms. 3r, etc., etc., as we go out. Now, this is where we start to link in this idea of the ln2, because as you see, what we're doing is we're coming along here, we just need to put it into those terms. So, let me just refer back to my previous workings. We're going to do that by so we are going to take all of these pairs and just get rid of those 2's by placing a 2 down there. And that will enable us to see that we actually have an addition, we actually have a sum of e squared over 2 pi e0, and then we have a minus 1 over r plus a 1 over 2r minus 1 over 3r plus a there plus, and so on. And you can see here this is the ln2 if I factorize out the r. Sorry, e squared over 2 pi e0. Good. Now, what we have here in the original thing was it said alpha over r, minus alpha over r. So if I take, remember, ln2 is 1 minus the half plus a third, 1 minus the half plus a third, so I need a minus out of that. And of course, I hope you can see it, this is minus alpha over r quite easily. So those r's go, those positives go. So actually alpha is equal to e squared over 2 pi e0 ln2, which is in effect 1.6 times 10 to the minus 19 squared ln2 divided by 2 pi 8.85 times 10 to the minus 12, giving us a grand total of 3.2 times 10 to the minus 28 joule meters. Ooh, so a lot of maths, a lot of identities to just sort of steer through and try and deal with. Okay, doesn't stop there. Second part says we're looking for the external forces, and it gives us a differential, and use that to find out the magnitude of F. Right, how do we do this? Right, here's some ideas for you. Number one, of course, you differentiate, but it might be an idea, because you can see E in there, to work out the E, what E is in terms of R0, and then what R is in terms of E. That might be your first point of call. And then 2, use a binomial expansion. There are 2. Okay, so we're looking to work out how we find out the force using these 2 ideas. First of all, find an expression for the strain, and then use the binomial expansion to work it through after differentiating, which it asks us to. So, spare bit of paper here, might need a bit of work. Let's first differentiate the function EP by dr, and that gives us the differential of d by dr minus alpha over r plus alpha r naught to the 8 over 9r to the 9. Okay then, so we take the, so this becomes minus 2, multiply through by minus 2, take the minus 1 and then multiply through by it, so that gives us plus alpha over r squared minus, but bring the 9 up, so that gives us minus 9 alpha r naught to the 8 over 9 r naught to the 10. So first bit, straightforward, those cancel, and that's fine, giving us, what's that? Let's factorise alpha out, 1 over r squared minus alpha r naught to the 8 over r to the 10. Right, but what do we have for the strain, as I suggested? So the strain is going to be r minus r naught over r naught, thereby giving us what's our expression for r naught. So that would be multiply through minus 1, so it's going to be 1 minus eta r naught is r, I believe, is that right? So multiply e r naught is r minus r naught, so therefore r is e plus 1 plus e equals r. Okay, tick. So what do we have here? Let's throw this back into there and see what we get. So that leaves us with, if that was an aside, we're now left with, of course, this is the force. So therefore the force is going to be alpha 1 over 1 minus eta squared r naught 1 minus eta squared minus alpha r naught to the 8 over r naught 1 minus eta to the 10 to the 10. Let's just make sure I haven't missed any terms out there. No, that's right. So this can drop with that to give me, oops, I did miss a term there, squared. So that can drop with that to give me r naught to the 2. So suddenly we have now alpha over r naught squared. And I have 1 minus eta to the minus 2 minus 1 minus eta to the minus 10. Is that right? Yes, that's right. Good. Now, if we binomially expand this, then that should give us 1 plus 2 eta, and this should give us minus 1 plus 10 eta. Alpha over r naught squared. Good. Let me just make sure I haven't missed anything out there. Good. Which equals alpha over r naught squared by, that goes with that, giving me minus 2, giving me right front. So it should be giving me an 8 at the front there, which is wherever I drop the sign, because we're looking for, going back to the equation, we give it 8 alpha eta over r naught squared. So let me just take a quick look. Alpha there, so that brings a minus into there. That is definitely a positive. So I throw it into there, giving me a minus. Oh, sorry, that's a plus. That's where I've gone wrong. That's a plus, giving me a minus, but giving me a plus 10. Good, which gives me 8 eta, which is exactly what I was after. QED. Okay, the next one says, in sodium, the atomic equilibrium is, so use the value to work out Young's modulus. Well, that hopefully should be easy. The hint, obviously, is stress over strain. And what is it? well, using the previous expression, the two previous expressions, we have Young's modulus is equal to force over area divided by strain. The expression for force is 8 alpha eta over R0 squared divided by the area divided by, so this was pi R0 squared. Sorry, coming back to my first one, it was 4f over pi R0 squared, because this is half of this, and divide all that by eta. So the etas disappear, giving me 32 alpha over pi R0 to the 4. Is that right? Let's just remind ourselves what it was in the first instance. Okay, good. And now we've got an expression for alpha, which was 3.2 times 10 to the minus 28 by 32 divided by pi and by the 3 times 10 to the minus 10 to the 4. And that should give us something like 4 times 10 to the 11 pascals. And of course, the last bit talks about that it may differ. And the reason why it differs is dislocation theory and the nature of three-dimensional objects. It's going to get more complicated, but it actually makes it less by a factor of 10 than that. Okay, hope that made sense.